How can current travel through the air and light a lamp without any wires? Today, we will build a wireless power transmission system based on the principle of electromagnetic induction. Just follow these steps and you'll uncover the mystery behind wireless power transmission. Let's get started. First, let's introduce the heart and engine of the system, two IRF2807 N-channel MOSFET transistors. They will be configured as the core of a push-pull oscillator circuit. These two MOSFETs act like high-speed switches working alternately. They convert direct current into high-frequency alternating current. This is the first step in generating an alternating magnetic field and enabling wireless power transfer. Next comes the circuit's energy gatekeeper, the LM781 voltage regulator. Our system requires a stable and clean 12-volt DC supply to operate. The LM7812 reduces a higher external input voltage down to a stable 12 volts. It also filters out voltage fluctuations. This provides a solid and reliable power foundation for the precision high-frequency oscillator circuit that follows. Now we set the key timing for the MOSFET switching action. These two 460 ohm resistors are connected to the MOSFET gates. Their main function is to limit the gate charging current. Together with other components, they control the speed at which the MOSFETs turn on and off. This switching speed and frequency are key parameters that determine transmission efficiency. Next comes the first key component that determines the frequency, 0.47 microfarad capacitor. It works together with an inductor that we will add later to form an LC resonant network. The capacitance, together with the inductance, predetermines the oscillation frequency range of the circuit. It is the foundation for generating high-frequency oscillation. Next, we add protection for the high-speed switching MOSFETs. These two BAV2060 components are fast recovery diodes. They are connected in reverse parallel between the MOSFET's drain and source. When the MOSFET switches off, the coil inductance can generate sharp reverse voltage spikes. These diodes quickly release that high voltage. This protects the MOSFET from being damaged by sudden voltage spikes. They act as guardians of the circuit's stability. Next, we add precise voltage controllers, 10-volt Zener diodes. They are typically connected in the MOSFET gate circuit. Their job is to clamp the gate voltage at around 10 volts. This prevents excessive drive voltage from damaging the MOSFET's gate oxide layer. At the same time, they ensure the MOSFET switches quickly between fully on and fully off. This helps reduce power loss. Now we add to 10 kilo-ohm resistors. They serve as gate pull-down resistors in the circuit. When the control signal disappears, they quickly pull the MOSFET gate voltage down to 0. This ensures the MOSFET turns off reliably. It also prevents accidental turn-on. They also work together with the previous 460 ohm resistors. Together they help shape the dynamic behavior of the driver circuit. Now we add the other half of the LC resonant network, the inductor. It works together with the 0.47 microfarad capacitor. Together they determine the main oscillation frequency. This LC network not only helps create oscillation, it also improves the output waveform. This makes the high-frequency current cleaner, and that increases the efficiency of magnetic field transmission. Now comes a key component, the transmitting coil. It acts as the energy transmission tower of the system. This large coil uses a 9+9 turn pancake design. It converts high-frequency alternating current into an alternating magnetic field radiating into space. The flat spiral design helps concentrate and spread the magnetic field. It is the key medium for short-range wireless power transmission. Here is the other half of the system, the receiving coil. It is made from 18 turns of wire. It is separate from the transmitter board. When it is placed within the alternating magnetic field generated by the transmitter coil, it cuts through magnetic field lines. This induces an AC voltage at the same frequency, allowing it to capture energy from the air. A 0.44 microfarad capacitor is connected in parallel across the receiving coil. This capacitor forms another resonant circuit with the coil's inductance. Its purpose is to match the resonant frequency of the receiver to the transmitter. When both circuits resonate together, the energy transfer efficiency increases significantly, allowing the distant bulb to shine brighter. Our energy tester, a 12-volt light bulb, is now in place. It is connected directly to the output of the receiving coil. The bulb plays a dual role here. First, it acts as a load that consumes electrical energy, converting it into light. Second, it serves as a visual indicator. Its brightness directly reflects the amount of power transmitted wirelessly. Finally, we inject power into the system. An external 18-volt DC supply is connected. The voltage is regulated down to a stable 12 volts by the LM7812. This powers the entire transmitter circuit. At this moment, all components are ready. A complete wireless energy transmission link has been formed. The transmitter board is powered on. The transmitting coil shows no obvious physical change. Now slowly bring the receiving coil with the bulb closer. As soon as the receiving coil enters the magnetic field, the bulb lights up. At that moment, energy truly travels through the air.